And minus 3 minus 1 gives you x to the power 4, right?
Right.
So now what we do is we need to work out 1 plus y dash squared. If you work out 1 plus y dash squared, so you square this. So we are going to square that. Once you square that, what you come up with is this. That's a bit of arithmetic, right? Like it's a minus b whole thing squared is equals to a squared minus 2ab plus b squared. So that's why I have a 2 here, right? So if you're careful, if you work that out and you simplify it, this is what you come up with. This is 5 over 6 squared, 3 over 10 squared because you have a squared, and then x to the power 8 because x to the power 4 squared is x to the power 8. 1 over x to the power 4 squared is 1 over x to the power 8. And you simplify the rest, and now you're adding 1. When you add 1, you come up with this. And that's a perfect square. That's a perfect square. Here I have checked it out for you. If you square this, you simply get this, you retrieve this. So all what we have today is the square root of a perfect square. If you take the square root of this, which is exactly the square root of 1 plus y dash squared square root. Minimize that. Okay. That's just, if we take the square root of that, that will give you exactly, then you don't need that. So what you have to work out is this integral. So if you work out that integral, it's just a straightforward integral to work out, but it gives you messy numbers, so that's it. Did you follow?
Yeah, follow. I'll just try. If you just go
No,
back.
no, 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 no. You copy it down because, and I'm going to post this stuff anyway. But I'm not. I don't want to post this lecture itself. I'll post the whole lecture without the talking business. All right. All this is there. You don't need the talking business. All you need is the working. So I'll post this anyway if you want me to. Not if you want me to. I'm going to post
Well,
all of
yeah,
this.
yeah.
I'm
If
going
you
to,
can post it, that'll be good.
yeah, I'm going to post this definitely. Uh, without my writing here, so it's clear. So what we have done is just recognize it is the square of a perfect square. It's a square of a number, and just you take the square root of that. That's what you get. It's a bit of a messy arithmetic, but you have to be very careful. I mean, look, this is good like for an assignment, but not for an exam because you'll be doing arithmetic, not maths.
That's exactly right.
They exercise in arithmetic, to be honest. But anyway, it's a good exercise
Yeah,
for you to sharpen your mind. It's very good. I like things like that. Now, what I want to do is I've worked a lot of problems here, and I've deliberately done this. I've taken from notes from James, from Stephen, from tutorial exercises, so you have a complete presentation of what this is about. Okay, now one thing is this. So we'll go back. It's all done here. I'm going to post all this. So let's go back and see what this is all about. This is about double integrals and polar coordinates, going from rectangular coordinates to polar coordinates. When you look at circular figures or spheres, it's always advantageous. Instead of working using, if you use rectangle, the Cartesian coordinates, it's very difficult. So here, it's very effective if you know how to convert it to polar coordinates. And I'm going to tell you which section you have to read up in your textbook. So that's the title of the lecture, and I'll use James's lectures, but this is basically the lecture today. How we change to polar coordinates in double integrals. So I want to tell you, please go to section 15.3 in your textbook, page 1063. I have it in front of me. And there is all the diagrams are given there. So I haven't drawn those diagrams, but you can read through and see how you divide the rectangular region which is obtained in polar coordinates, how you divide into small squares to approximate the integral. But look, basic understanding is all I need. You want to prove all this stuff, but you know how it works and what it means. So the idea is for you to read through page 1063 and just get it, just one page there, and they show you how you convert from rectangular coordinates, here rectangular coordinates, integral over r, f of xy, dA. This is how you convert it to polar coordinates. And one thing you must remember is this. This is called the Jacobian. R is the Jacobian here. And you have to remember this R term comes. But you will see exactly how effective this is when we work through problems. So the first thing for you must do is this.
Sorry, what was the page number again?
I'll tell you the page number is 1065.
Okay, I got to 1060 and I forgot the rest.
Yep, 1065, section 15.3. I don't want you to, sorry, 1063. They show you the region R, and it's depicted, the polar coordinates are depicted there, theta changing from alpha to beta, and the radius changing from alpha to b. So,
Dr. Rehes, what edition was that? Was that?
this is the point. This is the point. But I think in the old book, it is 15.4. In the new edition, which is, I'll tell you, this is metric edition 9E, it is section 15.3. But I think in the old edition, it's 15.4. So all you have to go to is double the integrals in polar coordinates and just refer to that. And it's just one page. I'm not going to ask you how you derive this formula. No way. I'm not going to ask you, but you must be familiar with this formula, how you work with it. And that's what I have done. I have worked through every single problem. I don't know, they have got problems from everywhere, but I thought it best is to work all these problems. Well, we can work more problems down the track, but here I'm looking at the more difficult problems where you need to understand the fundamentals. So here, you're going from xy, which is the Cartesian coordinate system, to the polar. In the polar, you have again two parameters, theta and radius. Theta and radius. That's important. So here you're given f is a continuous function on a polar rectangle. And you want to see what a polar rectangle is, go to page 1063. It's very well shown there what you mean by a polar rectangle. Now we want to integrate this function f of xy dA, where R is a polar rectangle. And your R changes from A to B. A is greater than 0, definitely. And your theta varies from alpha to b. Mind you, beta minus alpha must be greater than 0, less than 2 pi. So that's very important. And this is so important. You have to remember this formula. Fine, you can go to textbook, refer up if you forget, but you must know how to use it. So here's how we are going to use it. And I've given you a second equation which comes into fruition later on, but not for the time being. So first of all, let's see how we work with this particular integral. Say you're working on a circular region here. You can draw R. So here's your function, x squared minus 2y is like a surface, right? And if you were to, you're integrating this over this region R. So you have some surface, we'll draw this circle. I mean, roughly draw it, what it means. So you have a circle that here, I'm going to draw this here. The radius varies from 2 to 4. So that's on your XY plane. That's your XY plane. And on this is defined a function. You have some kind of function on this. So you're trying to integrate this function over this R. What is your R? Over this region. So you're projecting this onto this region here. You need a basic idea of it. I mean, drawing pictures is one thing, but to really understand what's going on is a different thing. So what you're trying to do, and this is like your function is Z, which is a function of xy, or you can call it f of xy. You're integrating that function over R. So here's your R. Now I'll work a lot of problems with you to show how these things really work. Now you're given this, so I'm just going to erase what I had, all the rubbish I have written here. And we are going to get down to solving this problem. So we are going to use this formula. Just this formula, we are going to use this formula. That's all. So what you do is, you are integrating x squared minus xy over R. Now, to convert it to polar coordinates, you substitute for x. Now, here you have like a circle where the radius varies between 2 and 4. Because x squared plus y squared is radius squared. So you have your, if you parameterize it, you get x is equals to r cos theta. Y is equals to r sine theta. So your radius r, so you have your x squared plus y squared is equals to r squared. And r squared goes between 4 and 16. So in other words, your r is less than equals to 2, greater than equals to 1. That's not hard. And your theta, you must remember, your theta goes a full circle. Theta is less than equals to 2 pi, greater than equals to 0, because you're integrating, the projection is on this r. So when you go around a full circle, theta varies from 0 to 2 pi. But you must remember here that one thing you have to remember is this. You want to integrate this where y is greater than 0. So if y is greater than 0, let me draw it here. Y is greater than 0 only in the top half. And hence, you have to restrict your theta to pi. Did you get that? Where's y greater than 0? Here. That's your x-axis. So you're integrating around this circle. And your radius changes from, we'll draw another circle. So I'm going to just take this rubbish out here. So you're really integrating here. You're really integrating. You have to be careful. Radius going from 1 to 2. Radius is non-negative. So your radius goes from 1 to 2 and your theta varies from 0 to pi. Why? Because you want the region y greater than 0. Did you follow that? Hello? No. You can't be on the fence. Yes or no? You know what I mean? Look.
Can you just redraw the diagram again?
I will redraw the diagram again.
I think I followed.
Yep, wait. Okay.
A second explanation might make sure I'm 100% following.
Yep.
It was going from radius 1 to 2. And
Yeah. Now listen. X squared plus y squared is less than equals to 16, greater than equals to 4. So the radius squared goes from 4 to 16. So r
So
goes,
4 is r squared.
yeah,
And then you would square root it, and that's how you get the 2.
absolutely. And y is greater than 0. So we'll draw this out. I'm finding it difficult on this because I can't touch the screen here. It just plays hell. And your r goes from, let me draw it properly. Your r goes from 1 to 2, and your theta goes from 0 to pi. Why? Because the region is greater than 0, it's bounded below by y. Here's your y-axis. Y must be greater than 0. Where is y greater than 0? Just here. And without this lower boundary here, I can't take this out, it'll all go out. So you're integrating over this region where I have depicted it. Can you see that? Did you follow that?
Yeah, follow
Yeah.
that.
Right.
So the cos theta sine theta that you've assigned to x and y, that's
You're right.
standard?
Because when you're looking at a circle, the parametrization of a circle,
Whenever it's circle, it's always cos and sine because
Right.
of the shape that you just drew up.
yeah, absolutely.
And the r is dependent on the boundaries, which
R is the radius. R is the radius.
Yeah.
Because
Okay.
you have a circle, right? You can describe a quarter of a circle. Say you want to describe, if you want to describe this part of the circle, say you have a circle like that. It's a circle, imagine it. Huh? That's the radius. Now, if you want to describe this circle here, its radius is r, but your theta is less than equals to pi by 4 and greater than equals to 0. Did you follow?
Yes.
If you want to follow, if you want to depict this circle here, and your theta is always less than equals to 2 pi greater than equals to 0 in this case like this. All right?
Yes.
So all what you do now is to substitute for x and y. Substitute for x and y where? In this function. X is r cos theta. So x squared is r squared cos squared theta
Mm-hmm.
minus 2y, 2r sine theta.
Mm-hmm.
Bracket. Now remember, you're going from dA, what dA is actually is like dx dy, right? You're going from that to the polar coordinate system. When you go to the polar coordinate system, your dA is equals to r dr d theta. Must remember that. They have derived that in that book, in the book on page 1063. So the element in this, in the polar rectangle just becomes r dr d theta. You can't forget, don't go and drop this r here. You can't drop the r. You have to involve this r.
Yeah. And in the diagram, the circle is at radius 2 and the outer circle is at radius 4. Is that correct? Or
no.
is the inner one
right.
the unit?
Oh,
the inner
that-
one the unit?
You really made my day. Good. 2 to 4, okay? Thank you. Let's start
I think I might have a different version of the textbook because I think
Yeah,
I found
yeah.
a problem. But
Yeah,
it's
but
radius 1 to radius 2.
it doesn't matter. It doesn't
It's
matter.
like 4. Okay.
Yeah,
It's the same type of question. Yeah.
It's the same type of question. It's the same type, So now I don't want to muck around trying to expand this something. Anyway, that's correct. So that's what I have put here. This is 4 to 16. Really, in this problem, it should have been, you're good, you corrected me. The problem should have been, I'm sorry here, x squared plus y squared is less than equals to 4, greater than equals to, how much was it? 1. Is that the way you have it? Is that what you have in the textbook?
Yeah, that's fine.
That's fine. It doesn't matter. So I must correct what I said earlier. So this radius goes from 4 to 1. But it doesn't matter. It doesn't matter. It's just a small mistake here. I should have just corrected this and put this as 4 and this as 1. That's all right. So now we integrate this. All we do is integrate. So if we integrate this, what we need is, so multiply this by r, throughout by r. Did you understand what I'm doing, Terry?
Yeah, I'm right.
Yeah,
I'm
yeah.
following.
Good. Now you multiply throughout by r. First you integrate with respect to dr. Of course your dθ is still there, but when you integrate with respect to r, you fix theta. You assume theta is fixed. So now you integrate this with respect to r. So you get minus r to the power 4. I don't know how I got a minus there. R to the power 4. That's a plus really. That's a plus. R to the power 4 over 4. Cos square theta minus 2 by 3 r cubed sine theta, integrate from 1 to 2. You integrate from 1 to 2. Is that clear?
Yeah,
Yep. Now you substitute 2 in. If you substitute, first put the top limit. You get 16 by 4. Put 2 here, you get 16 by 3 because you get 2 cubed, which is 8, times 2 is 16 by 3 sine theta. You kept theta fixed. Minus put the lower limit in. If I put the lower limit in, I get a minus of cos squared theta by 4 minus, put 1 here, you get 2/3 sine theta. Is that easy? Hello?
yeah,
That makes sense
that's
so far.
Yeah,
okay.
just straightforward. Now what you do is,
To be honest, I'm a little bit
Yeah.
unsure of the previous step. When we, okay, no, I think I answered it because this is cos squared theta we're dealing with, and it's in terms of theta. So
yeah. Now, cos squared theta is standard. What you do with cos squared theta is you express it at a double angle. Remember this. Cos squared theta, you can work it out, is equals to half plus half cos 2 theta. Now half cos 2 theta you can integrate. So instead of, I put a 16 there, anyway, it doesn't matter. So you work this part out. When you work this part out, you will get 16 by 4 minus cos squared by 4, which is 15 by 4, cos squared theta. So I have collected that term and that term, which gives me 15 by 4 cos squared theta. Cos squared theta is half plus half cos 2 theta, which you can integrate, no problem. Then you have a 16 by 3 minus sine theta, and you have a plus 2 by 3 sine theta, which gives you a minus 14 by 3 sine theta. Now, this is definitely 0. This becomes 0. That drops. Why? You get sine 2 theta, 0, that goes off. All what is left is this value. This goes to 0 because when you integrate sine, you get a cosine. And you get a cosine of pi, which is minus 1, 0, that also pops out. You can work that out and see. Integrate that and that pops out. All that is left is this 15 by 4 times half theta from 0 to pi. So that gives you 15 pi by 8. Is that clear?
No, that's all right. Just to
I'm
have
not
a couple
integrating
of,
yet.
Yep.
Okay.
Yeah.
Yeah.
That's fine. Can you just move it to the left a little bit so we can get the side that's slightly cut off?
I will relax. Thank you.
Yep. Is it okay if you scroll a little bit to the left?
Okay, sure.
Because it's slightly cut off. Other way.
Other way, yeah. Okay.
The
Is that
start
all
of the
right?
line. Yeah, it was just the start of the line was cut off.
The left-hand side. Yeah, we could not see the equal
Now can you see or what?
signs.
Is that okay?
Yeah. That's
Okay.
Much better.
That's better. But I'm going to work a whole heap of problems. That is today. And if you have questions from tutorial 9, I'll work through them, because writing up all that, I really don't have the time at this stage, because there are a few things I have to do.
Yep.
If I had time, pleasure. It's a pleasure, but I don't have time. But I'm willing to work through all the questions you have. Some send me questions, and that's the first thing I did. First answer the questions. There's heaps of problems here, and we're going to patiently work through these problems today and on Thursday. You go put all this aside and just correct me here. This should be really x squared. You know, I got this problem on the book, but I think they have taken it from 4 to 1. So just make this correction. When you see a region like x squared plus y squared, always use polar coordinates. And remember that you have to multiply it by r dr d theta. Your dA, which is dx dy in the rectangular system, is r dr d theta in the polar system. You must remember that. See how very effective. You can do this using the rectangular coordinate system. It's not hard. You can do it. But it's more effective using the polar system. It's more effective. As for the theory, just read through section 15.3 or 15.4 in the older version. In the newer version, it's on page 1060. It's just one page you have to read, 1.5 pages. And the change to polar coordinates is given on page 1064, the formula itself. The formula itself. Idea is to go work all throughout all these problems and tutorial questions. You have questions, just send me an email and I'll work through them at the lecture. No problem. No problem. Have you finished copying?
Yeah, we're up.
Okay, we'll get to the next question now. See now, you know, we know this answer. We looked at it and we know the answer is 2 by 3 pi r cubed. But here is how you use polar coordinates. You do the same thing. Here's your function f of xy. So that actually is equals to square root a squared minus x squared minus y squared. In other words, this is x squared plus y squared plus z squared. So you're integrating this. You have a surface, right, which is the top half of your sphere over this region, which is x squared plus y squared. So if you integrate, you find that's finding the volume of half of the sphere, and that volume is 2 by 3 pi r cubed. But you can show it using polar coordinates. They're otherwise just the intuitive proof of it, all right? So here, how do you go to polar coordinates? Quite easy. This is in your rectangular coordinate system. To go to polar coordinate, once again, you're dealing with circles. So it's x equals r cos theta, y is equals to r sine theta. And here, x squared plus y squared is less than a squared. So in other words, your x squared plus y squared, x squared, yeah, pen has got stuck for the, x squared plus y squared is less than a squared. So it goes from 0 to a squared. So the radius goes from 0 to a. So now we substitute. We write this in the polar form. Mind you, you're integrating around a complete circle. So theta goes from 0 to 2 pi. And your radius goes from 0 to a. a squared minus x squared minus y squared is simply a squared minus r squared. And don't forget your Jacobian r, then dr d theta. So dx dy is approximately r dr d theta in your polar coordinate system. And they show you how you derive that. So now you integrate this. First you integrate with respect to r. Now this is tricky. You have to get used to it. Don't use substitution all the time. First integrate this whole guy. Integrate this whole guy. If you integrate this whole guy with respect to r, is 3 by 2. You add 1. So when you differentiate, you must multiply by 2/3, because if you add 1, you come up with 3 by 2. Power 3 by 2. So when you differentiate, you get a half plus a 3 by 2 appearing in front. There is no 3 by 2. So you multiply by 2/3. So that's looked after. Now, then you differentiate the inside. You're lucky here, there is a r here. But we are going to get, when you differentiate this guy, the outer we have looked after by multiplying by 2/3. But the inner, you have a minus 2r. But we just have a r here. So you have to divide it by minus half, multiply by minus half to compensate for that. So cancel these two out to get minus 1/3. So now put in your limits of integration. You put a is 0. If you put a here, a squared minus a squared is 0. If you put 0 for r, you get a squared 3 by 2, but that minus and minus goes off. Minus 0. So what you come up with is this. Yeah, okay, that's fine. So if you have a plus 1/3, then
So
the lower limit gives you a positive, and you simply come up with that. Listen, you have to go and work through this, and don't go and doing this substitution, u is equals to so on and so forth. These things you should be able to manipulate easily. So that's exactly what the result. I mean, you're looking at the volume of the top half of a sphere whose radius is a, and that's 2 pi a cubed divided by 3. The whole sphere, the volume of a whole sphere of radius a is 4 pi by 3 a cubed. You can practice these problems and see what is the underlying philosophy behind this. Underlying philosophy. It's very easy once you get hold of what you're doing, especially in double integral. Usually in triple integrals also, they use spherical coordinates or cylinder coordinates or spherical coordinates. But here for the time being, we are looking at only polar coordinates. So once you become thorough with that, spherical coordinates become so easy. Just an extension. But one thing you must remember, here when you go from the Cartesian to the polar system, you multiply by r. Many forget that r, and that helps in your integration here. Mind you, if you didn't have an r here, then of course it's not easy. You get a sine inverse function coming, something like that. I forget that log formula or something. That table, it's a table formula. Here, if you have an r coming there, then it's wonderful. It's direct integration. Is that clear?
Yep, I'll have a go at that.
Yeah, but you have to work through this and you have to become expert at this. Then life is easy. Here's the next problem. I worked through these from the lectures everywhere I got it, and I thought I better go through all these problems. And I thought better write them down so you have it. I'm going to post this anyway on Views. That's what I'm going to do hereafter. The talking part is boring, just the working part. So you have to evaluate now here. You have to evaluate this integral and sketch a solid whose volume the integral represents. I mean, it is some surface like this. So you are integrating this over a rectangle. X going, yeah. And it's some surface. So Z is equals to 2 minus x squared minus y squared. So it's some surface like this. When x squared minus y is equals to 2, z equals to 0. So it's some surface you're integrating over this region. Here, x goes from 0 to 1, y goes from 0 to 1. I'm not going to ask you to draw a diagram, but that is basically what you're doing. What you're doing, you're integrating this function f of xy over this region, over that. That's your r. But this is a double integral. You don't have to go to polar coordinates here, because here it's a beautiful rectangle. It's just simple integral. X and y are independent here. Here x and y are independent. So what you do is, either you can integrate with respect to y first, and then with respect to x, or with respect to x, and then with respect to y. So if you integrate this with respect to x first, you keep y fixed. That's what this means. So integrate with respect to x, keeping y fixed. You get 2x minus x cubed by 3 minus xy squared, where the limits of integration was 0 to 1. Here's 0 to 1. So instead of x, you put 1, you get 2 minus 1/3 minus y squared. You put 0, you get 0 throughout. Now integrate with respect to y, and that's it. And that's your answer. First, you must know whether you're dealing with independent variables of integration, and whether it is a straightforward double integral where you can just integrate with respect to y first and respect to x. Is that clear?
Yep.
So you see something like this, don't jump and go to polar coordinates. There's nothing to do with polar coordinates. Here it's a simple double integral. Simple double integral. Now we worked a lot of double integrals last time, and we showed what the type 1 region, what the type 2 region was. Right?
The trick here is, Rehes, it says iterated integral.
Yeah, this is called the iterated integral.
Yeah, and that gives you the clue.
Yeah, absolutely. Absolutely.
Double integral.
Yeah. If you're said to work out this double and you're not said this iterated integral, then straight away you must know at once, looking at the problem, this is just iterated integral, right? X and y are independent here. Because your limits of integration are independent with respect to x, respect to y, right? You follow?
Yeah.
I'm taking several types of integrals, various times. I'm really putting a spoke into the wheel so that you really understand when you come to exams, you have no problem selecting what method you should use to solve problems, right? See, now
So
here.
basically saying for the polar integrals, whatever it's called, polar coordinates, only do that if it's like a circular type shapes. Those
Circular type shapes, and you're looking at surface integrals of volumes. I ask you to just work out that integral, but you must first, then here I'm just giving the limits of integration, not to 1, not to 1. It's just saying you're integrating over a square. Simple as that, where x and y are independent, right?
Yeah.
Here, just to I like to make things be confusing so that you can see clearly what's happening here. Here's another example. They're all taken from lecture here and there, but I took them so that I can explain everything in just one lecture. I mean, we have things to go, but for the time in all what we have done before and up to now, how we tie things up together. Here you're asked to integrate. Now, this is really a double integral, but that's by definition when you put dh, you have to integrate this over R2, over R, where R is defined as y changes from 0 to 1 and x changes from 0 to y. So you have a surface, y is equals your f of xy is equals to x root y squared minus x squared. you're integrating this function over this region. Now, you have to be very careful. Now this, you don't use polar coordinates. What you have got is this. You have y changes from 0 to 1. Here, y changes from 0 to 1. So I have to be very careful. That's your y-axis. That's your x-axis. So y changes from 0 to 1. And your x changes from 0 to y. So how do you write that integral out? You change your x from 0 to y. 0 to y. So you have x root of y squared minus x squared. That thing, nothing changes there. And you're integrating first with respect to x. So this is a type 2 region. And it is convex. Even you can do it over the other type 1. You can work this over type 1 even. No problem. Because it convex in both directions. So you're integrating x. Here x is 0. On this axis x is 0. And you're integrating that from here to here. So you're integrating from x equals 0 to x equals y. And then you change y from 0 to 1. So this is a type 2 region. If you can, but if you try working over a type 1 region, that integral will be difficult to take. That integral over a type 2 is easy. Maybe I did it over type 2. I'm not sure. No, I haven't done it. It probably becomes difficult over a type. Then you have to use a massive formula. So watch. You integrate from 0 to y. X goes from 0 to y. Then y changes from 0 to 1. Now this is standard integral. You see, you have x coming here. And you're integrating with respect to x. Beautiful. You can simply integrate this. This is simply to the power half. 3 by 2 multiplied by 2 by 3, same old trick. And you have a minus 2x. You have an x here, which is nice, which covers that. You have a minus 2, you multiply by minus half. That's it. So you have integrated that. If you were to integrate this with respect to y, it's a bit of a headache. Then x is a constant there. Then the formula is huge. You can go to your tables and see it is quite a long table if you integrate with respect to, but you must get the same answer anyway. So here we have got the integral. You go and practice that. You must know how to practice a square root. How do you spell integral of that? Dx. That's a straightforward. So this is x to the power 3 by 2, 2/3. So those are standard integral. I mean this to everyone. I'm not singling out anyone. Now, once you've done that, you just put in your limits of integration. Put in y. If you put in y here, y squared minus y squared is 0. No problem. Put a 0, everything is 0. Put a 0, that becomes 0. That's a y squared minus half 1/3 and becomes a plus because you're subtracting the lower limit. You have the upper limit f of y minus the lower limit of 0. So the lower limit 0, because there's a minus sign here, become plus. So it's a straightforward integral y to the power 4 by 12, 1 to 0. I mean it, you have to go and work all these problems out. Keep this as a reference and go and do these problems without looking at the solutions. Because you have to get used to integration fast. Then the exam is simple. But if you're going to get stuck in this minor integration, then it's going to be horrendous. So the good thing here is that when you're using a type 2 region, then this x out here is so convenient. It's very convenient. This is convenient. So convenient. But if you're integrating with respect to y, your x is a constant, then the square root of y squared minus x squared is a table integral. You have to check at the tables. It's not standard. It takes a fair bit of work, lighting logarithms and all that stuff. But they are table integrals anyway. Have finished copying?
Yeah.
Good. Go on to the next one. All types. Now watch here. Now here, this is a classic example. You have to integrate x cos y dA over this region y equals 0 to y equals x squared. So here's the region. Y equals, so here's the region we're referring to. It has got a bit monkey. Okay, here's the region here. I don't know whether you can see it, but maybe it starts writing. Take a bit of time. Okay, so we want to integrate over R. What is R? Bounded by y equals 0, x equals 1, y equals x squared. You can treat this as a type 2 or type 1 region. But here we are going to treat it as a type 1 region. So in other words, we are going to integrate over dA, y changes from, x changes from 0 to 1. X changes from 0 to 1. But your y changes from 0 to x squared. Yeah. So your y changes from 0 to x squared. So here we are treating as a type 1 region. You may try this using type 2 region also. So if we do that, we integrate for respect to y. Y changes from 0 to x squared. Here's the lower boundary to the upper boundary. And x changes from 0 to 1. Now, this is easy to integrate with respect to y. If we integrate this with respect to y, you simply get minus x sine y. Because if you integrate, I'm not sure. Yeah. Integral of cos is sine, because differential of sine is cos. I don't know why. Yeah, you don't have this plus sign here, so that's a plus. Check that out. Now, is that right? I think I'm right here.
Yep.
Yeah, I'm
I think
right. Yeah, I'm right.
Correction.
I'm correct. That's correct. So because you integrate with respect to y, if you integrate with respect to y, you get sine y, and your upper limit is x squared, lower limit is 0. You have a sine y. Derivative of sine y is cos y. So integral of cos y is simply sine y. That's a plus there. Sorry about that. Now put in the limits of integration. If you put in the limits of integration, this is what you get. You get a 0 is 0, and the top is x squared. So you have a x squared. So you put in x squared here, that's sine. So you have a sine squared, and that's a plus still. Sorry about that. Now you can integrate this. If you integrate this, here now you get a minus. You get a minus there because, and you're lucky you have an x here. All you have to do is divide by half, divide by 2 to compensate. Now differentiate this. If you differentiate this, the derivative of cos is minus sine. Correct? So that minus and minus goes off. Derivative of x squared is 2x. 2 and 2 cancels out to give you that. So now you put in your limits of integration. If you put 1, you have to put the lower limit first, top limit 1. So what will you have is half cos 1. Half cos 1. So I think there's a minus there, half cos 1, which is equals to minus half cos 1. And put the lower limit plus half. So I think it is half 1 minus cos 1. So let's check this out. First, you integrate this with respect to y. If you integrate cos with respect to y, you get sine y, because the derivative of sine is cos, and x is fixed here. Now here the limits of integration 0 to x squared. Put x squared here, you get x sine x squared dx. At 0, sine 0 is 0. Now integrate this. This is what you come up with. Sorry for the error. Sorry for mistake. Did you get it? Hello?
Yeah, I'm just trying to find that spot.
Yeah.
Now watch. Now we are going to use, yeah, it should be the same answer. I don't know what, I made a mistake somewhere. Now you can use this method also. You can use the other method. Okay, I'm going to draw this out for you. So you have that. So you have x equals your top one. We'll check it out. X is equal to root y. Here we use region, type 1 region. Now we are going to use the type 2 region. In the type 2 region, we are going to integrate x from here to here. So x changes from root y to 1. So we are going to do the same integral. So x changes from root y to 1. Here, can you see x is root y to 1? And
Yeah.
y changes from 0 to 1. Right? So if you integrate that, this is what we get. First, we integrate with respect to x. If we integrate with respect to x, keep y a constant. So you simply have x squared. See, this is the thing, x squared by 2. I made a mistake. X squared by 2. Root y to 1. So putting 1, you got 1 cos y. Minus, put now, instead of x, you put root y. You get y, because root y squared is y. Y by 2 cos y. Now, if you integrate this, now integrate this. Now, the problem, you have to be careful. This is a direct integral. This integral, you have to do it by parts. So you do it by parts. So I will just integrate 0 to 1 y by, I forget the half, leave half alone, cos y dy. Leave the half alone. Let us substitute. Let's work out this. So you first integrate cos. If you integrate cos, you get y sine y. Minus. And you put in the limits of integration, 0 to 1. Next, you integrate 0 to 1. This is u dv. Next, you need, that is sine y, differentiate y. If you differentiate y, you simply get sine y dy. So you get rid of your y. So this is simply equals to put 1 here, you get sine 1 minus 0, that goes off at 0. This is simply plus cos y. If you integrate sine y, you get cos y. And put in the limits of integration here, you get sine 1 plus cos 1 minus 1, because cos of 0 is 1. So you have got this integral. Therefore, that integral is so much. Now all you have to do is substitute here. You get a half sine 1, and then you have a half here. I did half of sine 1 that goes off, that drops off.
I'm a bit
Don't
rusty
worry.
with my integration by
I'll do it for
parts.
you.
That was in
Yep.
maths
Yep.
1B,
I'll do
wasn't
it for you. All right. I'll do it for you. Okay.
Mm.
Pleasure. I really like when someone tells me, and I really appreciate that. I appreciate it. I'm going to do it again. I think not only you, there might be a few more, but they
Thank
won't
you.
say.
I think, yeah, I've copied that down. I think I'm just
Yeah.
forgetting the general.
I'm going to show you how you do it. Suppose you have UDV, all right? To integrate this by part, this is the formula. U integrate dV, you get a V, minus, now differentiate U and multiply it by V. We'll do a simple example, okay? Right? Now that's the
the general
integration
form.
by parts. Integration by parts. Now we'll do this simple example, what we did now. So I'm going to take, we want to work out this. This is what we are after. Minus integral naught to y by 2 cos y dy. This is what we need, right? So what I'm going to do is I'm going to write this as minus half integral naught to 1 y cos y. Okay?
Yep.
That's a constant out. So all we have to do is to deal with this part. Let us work this part out. Right? Then you multiply by minus half. Okay? Right?
Take the constants out.
So now let's work that out by parts. Let's work that out by parts. Integral naught to 1 y cos y. You can choose either as your u, e, or v. But here it is good to choose y as your u and you use this as dv. Because what we're trying to do is get rid of your y. We want to get rid of y. So we are using the formula now. u, v. I'm going to write the formula again. So the limit of integration is 0 to 1 minus integral v du naught to 1. This is equals to your u is y, no problem. But your dv is cos y. dv is cos y. So that in other words, dv for dy is cos y, which implies that your v, which is a function of y, is simply sine y. Because if you differentiate sine y, you get cos y. You got it?
Yep.
Right. So it's integrating.
Yeah. So now you put sine y here. 0 to 1 minus, now your v is sine y, so we write your minus sign. So I'm writing it here, so I have space to write integral naught to 1. Instead of v, I'm writing sine y. Now your y is u equals y. Therefore, du is equals to dy. So, instead of your du, you have dy. So, what you have here is, you have a straightforward integral y equals sine y from 0 to 1. I must put a y here. Minus, now the integral of sine is cosine, but the derivative of cosine is minus sine, so I need a plus cos. Because if you differentiate cos now, you get a minus sign, exactly what we have here in the integrand. Right? You have to look, you can't say right and just, it's not magic, it won't go off. You have to go and work problems. You understand? So now we substitute 1. If you substitute 1, you get sine 1. Put 0, that's 0, plus cos 1 minus, put the lower limit, is cos of 0 is 1. Now if you multiply this by minus half, now I left this minus half out. See? I left that minus half out just for convenience.
Right.
You know?
Yep.
Now if you put everything together, you get the correct answer, and check. Maybe I have made a couple of arithmetic mistakes, but you check that out. But you go sit down and do these problems. You have to practice these problems.
Yep.
The things become so easy once you learn this stuff, you know. That's why I thought I do a lot different types of problems. It's not only learning the theory and how to apply whether they are iterated double integrals, whether they are surface integrals. Soon I'll be working surface integrals, but this is a 4-hour lecture. We can't do everything in just 2 hours if you are to really understand things. So now, here's another case. Find the volume of a given solid. Then here you're given the vertices. Over this triangle. Here are the vertices of this triangle. So the one vertex is 1, 1, that's 1, 1. This is 1, 2, this is 4, 1. So you have a surface over this, some surface over this. So if you were to draw this in the XY plane, you have something like this, and then you have a surface over this. All you need to know is the projected area. You want to find the volume of this function. Here's your function, z equals xy. It's kind of some hyperbola, right? Say xy itself, the function xy itself goes like this. I mean, function xy itself goes like that. But you have to find, and that's your z function. And it's, so the z function is, in other words, your f of xy is equals to xy. So you're integrating this function over this region R. Here you don't need polar coordinates. It works with rectangular coordinates. So the whole idea here is what type of region you're going to treat. You should get the same answer because this is convex in both directions. No problem. It's convex in.
A quick question. How could we quickly figure out the linear equation there, y equals?
Yeah, that's a good question. Now, I have worked it out, but I'll tell you, that's a good question. Now, here are the vertices. Now, if you look at, you're going from 1, 1 to 4, 1. Here's 1, 1. Here's 4, 1. Here, y is equals to 1. Right? Y is always 1. Now, here, you look at this vertex and this vertex. This is 1, 2. This is...
Yep. So
how much is this? Is y is 2, y is 1 here. X equals 1. This line is x equals 1. Now, how do you work? I like when you ask me questions. I really appreciate. Now let's derive. Now all we need to do is this line. So in general, that line is y equals mx plus c. In general, right? That's a general equation of a straight line. Now, when x equals 4, y equals 1. So x equals 4, y is equals to 1. Substitute. 1 is equals to 4m plus cos.
Right. Yep.
Now, and when x is equals to 2, y equals 1. When x is equals to 1, y equals 2. So you have 2m when x is equals to 1. Sorry.
Oh, just one
plus
m.
c.
Yeah.
Now you solve this equation. If you solve this equation, you get m is equals to minus 1/3 and c is equals to 7/3.
Of course. Yeah, that makes
right?
sense.
And that's a very good question, because it's bad to, if you don't know something, you must ask. It could be the simplest thing, just ask. Then you solve all your problems. So now
I suppose another way, if I wanted to, I could have quickly found
the gradient, you can find the gradient, absolutely.
and that way I only have to solve for C.
Yeah, solve for C, absolutely. That's another way, right? Just find the gradient, and the gradient is minus 1/3 here. Rise over run, right? So
Yeah.
so it is 1 minus 2 divided by 4 minus 1, which is minus 1/3, right? Or like you said, then only find the intercept. That's all. Now watch. So now we have gone through that. Now I'm going to take this stuff out. That's what I like Surface Pro. You can erase things out and all. Now, I am going to treat this as a type 1 integral. Your x changes from 1 to 4. There you are. Type 1 region. You must get the same answer, type 1 region. Because it is convex in both directions. It convex in both directions. Now, you integrate xy, it's there, that's your function f of xy. Now you integrate with respect to y first. Y changes from lower limit 1 to a point here. You changes from 1 to a function of x here. So y changes from 1 to minus 1/3 x plus 7/3. Now you integrate this. You integrate this. Homework, you integrate this. A bit of hard yakka, but it doesn't matter. Just integrate. You want to integrate it? Okay, here we are. We'll integrate that. V is equals to 1 to 4. Now, integrate with respect to y. So you have xy squared divided by 2 integral lower limit is 1, upper limit is minus 1/3 x plus 7/3. After a while, this starts plus 7/3 dx. So that's equals to 1 to 4. X is x by 2, leave it, that's common. You have a y squared, which is minus 1/3 x plus 7/3 whole thing squared dx. So your 3 is common. So it becomes integral 1 to 4 x by 3 squared that becomes an 18 minus x plus 7 squared dx. So that's it.
I'm a little bit unsure of, don't we also have to put 1 in for the lower limit?
You're right. You are very good. That's good.
Oh.
Yeah, I forgot. You're right. Thank you. So I had to put a 1 to the lower limit. So we put that. Then you have to, we'll do it at once. So I'm going to put a bracket here then, right?
Good. Oh.
I'm going to put a bracket here. Because that x by 2 is like a constant now, so I can leave it there. Now I put 1 for the lower limit. If I put 1 for the lower limit, I get half here. Is that right?
Yep. Mm-hmm.
So what we have is this. Then you can't, you have to do it a bit different. So you have x by 2 bracket. Then we square this. You have 1/9 x squared plus, if you multiply this, that's twice that. So you have 3 times that, that is 7/9. 7/9 is minus 14/9. Minus 14/9 x. Then you have to square this. That is 49/9. Minus half. Dx. So this is equals to, this is a half, no? That's all right. So it's 1 to 4 x by 2, 1/9 x squared minus 14 by x by 9. You take this half, that's a 9 there, that's 18. So it's a bit of a problem. You have to work that. And doesn't matter. Plus, this is 298. That's 90, 98. 2, 4, 18, 198 minus 1 divided by 9 by 18. Where the common factor is 18 here. So you have dx here. So that's equals to integral 1 to 4 x by 2. Check the arithmetic, 1 by 9 x squared minus 14 x by 9 plus 97 by 18 dx. So then you just substitute, you just work out this integral. So you have right, integral 1 to 4 x cubed by 18 minus, here there was 14, 14 x squared by 18. Here you have plus 97 by 36. You have 1 to 4. Now just integrate this straight away. If you integrate this, you get x to the power 4. Then you need 4 times, that is 72, minus x cubed. So that will give me 14x cubed. You multiply by 3, so you need another 54 here. So if you differentiate this, that will give me 18 there. And you have another what? You have x here. So if you integrate, you get 97 over 72 x squared. Now substitute 1 to 4. It's a bit of a hard yakka, but it is just arithmetic here. All right? Okay?
Yeah.
All right?
Yeah, I'm following.
Yeah. But this is just straightforward integration, straightforward integration. And look, I might have made an arithmetic mistake. It doesn't matter. So either you can, the main thing is this, either you can write this as a, now this is the type 1, you can write this as a type 2 region also. You can write that here as a type 2 region. If you work it as a type 2 region, it could be easier. Because here you have fractions, here you don't have fractions. You follow that? Did you follow?
Yeah.
Excuse me, rehearsed.
Yeah.
Should the constant be 1 or a half? Because I think you take x on 2 to the front.
We are here. Where was it?
So it's integrate from 1 to 4. Oh no! Just screw down a little, screw up a little bit. Yes.
Here.
Second row, yeah.
Yeah, but exchanges from 1 to 4. Is that the problem?
Oh, hold on.
Here exchanges from 1 to 4.
Yes, that part is perfect. Okay, just down a little bit, please.
Here.
A little bit down again.
Here.
Yes. Okay. So in the red lines, the second line.
This line.
Yes, that's right. That's right. And the constant part, you put down, take away half to the end. Should that be 1?
That should be 1, is it? Yeah. So when I put in, so I substituted 1 here, and you're right. If I substitute 1 here, I get, how much will I get if I put 1 in here? So I have x by 2, y squared by 2, so top is correct. Now if I put 1 here, I put the top limit. If I put the top limit here, how much do I get? Let me check that out, right? Because I'm not very good at it. Okay. You put the top limit first. X by 2 is out, no problem. So put the top limit in. What will you get? The bottom limit is 1. Do you agree?
Yep.
Right. If you put the top limit in, what you will get is minus 1/3 x plus 7 by 3 squared minus, now put the bottom limit in. How much will you get?
Yeah, just
That's 1. How do you get 1 here?
1.
Put the bottom limit. Y is 1. X is 1. So, no, I put the top limit here, y squared. I'm substituting for y squared here. Now I substitute for y equals 1 here.
Mm.
Okay, sorry, I have to get that back there. Because I'm taking this integral here. I'm taking this integral. So when I substitute the lower limit for y equals 1, what will I get? Your x by 2 is out.
So just
What
y
will I
squared.
get? 1. It's just
Yeah.
1.
Becomes 1 squared. Yeah.
Thank you. Now you work that out. Can you work that out? Hello?
No problem.
Thank you. That's very good. That's very good. Now work that out. Now this is not a difficult integral. You do this for homework. Everyone. That's easy, squaring. This probably is much easier. We'll try that one out. We'll try that one because that hasn't got any fractions. So if you integrate that v, you simply get 1 to 2. If you integrate, you're getting a fraction because you're x squared by 2 still for all. It doesn't matter. You should get the same answer. You try this out. Work, find the volume using that, find the volume using that, and
Yep.
they must be identical. Look, if you do it, then you learn. If I do it, you're just repeating. All right? And
No
it's
problem.
good practice for you to work out integration. Okay? Not that I'm lazy or anything, but yeah, partly lazy also. But, you know, integrals you should be able to take. It's good practice. That is done anyway. Anyway, thanks a lot. You know, sometimes when you write on this, you tend to make mistakes, but you must avoid mistakes. If you have any questions, I'll post tutorial 10. I think must have posted tutorial 11. You have any question, just tell me. So I'll work it at the lectures here so that we all work together. So now here's another question here. Your internet is unstable. It doesn't matter. It's always unstable anyway. So here's, find the area bounded by the coordinate planes B part. Where is B part? Yeah, the coordinate planes. Find the volume. You have to find the volume bounded by the coordinate planes and this plane. So here's the other coordinate planes. This is one coordinate plane. Here's another coordinate plane, and here's another coordinate plane. So you have 3 coordinate planes, and here you have this surface here. So you have to find the volume. So once again, you don't have to use polar coordinates, only it's just rectangular coordinates. So this is the region you're after. Now someone asked me, so your x-intercept is y equals z equals 0. So x equals 2. Your y-intercept is when x is 0, z is 0, you get your y-intercept, which is 3. Just look at that. And your z-intercept is when x is 0, y is 0, z is 6. So now you have to find the volume of this. You have to find the volume. To find the volume, you just integrate this. 0 to 2, 0 to minus 3 by 2. So you write this, we are integrating over this region here. You're integrating over this region. So to integrate over this region, you write the equation of this line. Just like we did earlier on, the equation of that line is minus 3 by 2, x plus 3. So to find the volume, this is what we do. We just integrate this out from 0 to that and exchanges from 0 to 2. So what we get is simply 3. Simply 3. So that's the first part. That's the first part. That's the first part. This is the second part. Yeah, we want to find the volume over that. Right. Yeah. So wait. I have to write this sum minus 3x minus 2y. Right. Just a simple, there is a mistake here. To find the, I'm just taking this integral. To find the volume, this is what we do. Volume. To find the volume, we integrate this. Your x changes from 0 to 2. Your y changes from minus 3 by 2 to x. Sorry, from 0 to minus 3 by 2x plus 3. And this is the volume, x minus 3x minus 2y. So you're integrating the first one with respect to y, then with respect to x. So I made a mistake. The volume here, I must multiply it by z, which is f of xy, which is equals to z, and z is equals to 6 minus 3x minus 2y. Can you please correct that? Hello? Hello?
Yep, doing that now.
Yep, just correct that. So what you have to do is you have to work out this integral. So you have to integrate this with respect to y. You have to integrate this with respect to y, then with respect to x. And you also do that. Do that for homework. Can you do that?
Just confirming,
Do that.
Is that function there s of x, y equals z?
Yeah.
Yeah.
I'll write it. So to find the volume, what we have to do is to integrate this from naught to, actually have to integrate this, we will write it properly down. You have to integrate this over d, z, dy dx. Or I must write this, dA. So your z here is a function of f of xy. In this case, it will give us the volume. I don't know why I forgot to put that in. I forgot to put, here what I have done actually is found this area here. Just found this area. That's obvious. But to find the volume, you have to multiply by the function z. Is that clear? Hello?
Yep.
Yeah.
Thank you.
Yep. So there are things, okay, I've been trying to do this very fast with the, actually yesterday, and so there are some mistakes. I went today and did some photostats and just pasted everything in here. So we look at the examples also. Here. You have to evaluate this. These are also from the tutorials and class exercises, but I picked up the more important ones. Evaluate the following integral, 0 to 1, and you have to first sketch this. You have by reversing the order of integration. Just trying to integrate this. Now here, actually this is x here. Inside this is square root of 1 plus x squared. So that's a mistype. Now, you have to do this by reversing the order of integration. So instead of here, it is defined as a type 2. This is type 2. But using a type 2, it's not easy to work this out using type 2, but using a type 1 is probably easier. So what we have here is this. Just look at this integral. You're integrating this first with respect to x. So x changes from arc sine y, here's arc sine y. See, the graph of arc sine y, sine inverse y goes like this. Here's minus pi by 2, here's pi by 2. Sine inverse x is defined between minus pi by 2 and plus pi by 2.
Right, yeah.
Yeah, this is sine inverse x, okay? I'm sorry, that is tan. I drew tan out. Sine goes like this. Sine goes from, at pi by 2 it is 1. I'm sorry, that is sine. This is sine. So you're integrating this from this point here, somewhere here, x equals arc sine y. So a point on that line, on this curve here. So in fact, it should be like this. It should be like this. This is arc sine y. This is arc sine. Or y is equal to sine x. So you can write x equals to sine inverse y. Because x goes from minus pi by 2 to plus pi by 2. And you must remember that x goes from minus pi by 2 to plus pi by 2. So arc sine 1 is pi by 2. That refers to x equal to pi by 2. So you're integrating from this point to that point. Now what you do is you reverse the order of integration. So in this given integral, your y changes from 0 to 1, whereas your x changes from arc sine x to pi by 2. Now we are going to reverse the order of integration. If you reverse the order of integration, your y goes from 0 to sine x. So y as a function of x is sine x. And your x goes from 0 to pi by 2. It goes from 0 to pi by 2. Now it is easy to integrate this. This is simple to integrate. Because first you integrate this with respect to y, keeping x fixed. If you integrate with respect to y, you dy becomes y, and put the limits of integration. Sine x, lower limit is 0. So you get that. Now this is straightforward. The derivative, so we integrate, how do you integrate this? First 3 by 2, then multiply by 2/3, then you have to multiply by, because when you differentiate cos, you get 2 cos x minus sine x. But you have a cos x sine x here. But in addition, when you differentiate, you have a minus 2. To compensate for that, you put a minus half. So that and that cancels off, minus 1/3, and this is the direct integral. Just put pi by 2. This is, hello, yes?
Just got a question about the first line of working. To the next line of working, the first line of working to the second line of working.
Right.
We find that it the inner integral, the dy integral, that I just wanted to confirm, we have y cos x at the beginning of the next line down because we are integrating with regards to y.
Y. Yeah. Where you keep x fixed, then you simply keep cos x.
So we treat that entire thing as a constant, essentially. Like that whole
as a constant.
Is like a constant.
You treat it like a constant. 2, 3, something like that.
Great, yeah.
Whole thing is a constant.
No problem.
You integrate with respect to y. You get y. Put the top limit sine x, bottom limit 0. You simply get a sine x there. Okay? Simply get a, put for top limits sine x, bottom limit 0. So you put, what will happen is you get a sine x cos x root of 1 plus cos squared x. Bottom limit put 0 for y, then all that is 0. So all what is left is what you get from the top limit. You follow?
Yep.
Yep. Next is all just get used to this square root business without putting all these substitutions. So now you substitute pi by 2. If you substitute pi by 2 for cos square, cos pi by 2 is 0. So that pops out. At 0, it is 1. Cos of 0 is 1. So you have 2 with a minus sign. So you have plus 1/3. And you have a 3 by 2 here. So you have a 2 root 2 minus 1 1/3. Check that out. This is correct. Correct? Right?
I think so. Looks right.
Now see the next one. Now some of these integrals.
Sorry, could we just
Yeah, it is. It's
almost
You're
finished?
writing. You're writing.
Sorry.
you're still, no worries. I have all the time. I have all the time.
Thank you very much.
No problem.
You're putting all this up, aren't you, Rez?
Of course I'm putting this up.
Right.
Where there I have made some mistakes, like the volume, I forgot that. You put it in, all right?
Yeah.
Yeah.
Yeah. I forgot that. I don't know how I managed for this. So,
Okay.
you have to go work through all these problems. But work all look, what else can we say? Just a few changes and you know your fundamentals, you're through. Simple as that. No problem. Now here's an integral. Now, yeah, what I'm going to do is this. When I finish this one, this I'm leaving for Thursday. Is that all right?
Yep.
Surface integrals, because I can go like a train, but I want you to understand the first few questions and also go through your tutorial 10. And I'll post tutorial 11. You just go through that and try some problems. What you can't, you let me know and I'll work them. Because this stuff is also for next week tutorial, right? But when I finish this surface integrals, I leave for Thursday. That's fine, because I'm also getting a bit tired, right? If you don't mind.
No, you're right.
No problem.
So, but no, it doesn't mean that you can rest till Thursday. You better go through all these problems and work through all these problems. Any questions you have, let me know on Thursday. I'll revisit this section again. Now watch. If you want to integrate this here, you're integrating that by reversing the order of integration. If you try a double integral, you can't work it out. The best method, the best technique is to reverse the order of integration. Problem solved. You try to integrate this now.
Can you just read out that question? It's just very small. I can't read it.
Yeah.
It's just the integral bit. Yep, that's better.
Yeah. Well, very good, the Surface Pro. If it works, I was teaching on Surface Pro this morning, it got stuck. So I had to revert to using my laptop.
Thank you.
It has its moods, this Surface Pro has its moods. You know. So, look, you try to integrate this as it is. It's impossible, virtually impossible, if you integrate. But you can integrate this using reversing the order of integration. First of all, look, I drew this picture out. Here you are integrating with respect to x first. X changes from 3y to x equals 3. So it's changing from here to here. So this is a type 2 region. You're treating it as a type 2, and it's virtually impossible. Virtually impossible. No I here. Impossible. To evaluate this integral. Virtually impossible. Where did it vanish? That has gone. Yeah, we are here. We are here. But if you treat it as a type 1, now I'm going to change the order of integration. To change the order of integration, you write y as a function of x. So here, look, you're given, I must expand this, x equals 3y. Solve this in terms of x. Solve in terms of x, you get y equals 3. So you're changing the order of integration from here to here. So your y changes from 0 to y equals to x by 3. And your x changes from 0 to 3. So here we are, quite easy. X changes from 0 to 3. Y changes from 0 to x. Now integrate with respect to y. You keep e to the power x squared constant. Now you integrate, you got a y here. You got a y here. Now put in this x by 3 into y, 0. So if you put that at 0, that is 0. At x by 3, that's simply x by, and beautiful, because this, when you integrate this x squared, that x compensates it. The integral of this is simply e to the power x squared. If you don't have the 3, then you need a half here, because if you differentiate this, you get 2x over 2. So you got the x there. See, you have an x here. That's good. So when you integrate and you have a further 1/3 here, you need the third here. Now put in the limits of integration. You try without reversing the order of integration. It's virtually impossible. But if you change the order of integration, reverse the order of integration, trivial. So if someone gives you a problem, me or someone gives you a problem, and you find it, oh, this is difficult, then go and change the order of integration. But you must know how to change the order of integration. That's very important to know how you change the order of integration. First, draw out the picture of what type of region you're using, whether it's a type 1 or a type 2. You have to go, that's what I don't want to do surface integrals today, because you have to become a master at this. Picking the what choice you're going to make, whether it's a type 1 region or type 2 region. We did double integrals, we did polar integrals, but we are going to combine everything to work out surface integrals on Thursday. But your job is to tell me over the next couple of days, I'll send the assignment tomorrow evening or Thursday, I'll post the assignment. That's no problem. That's no problem. And you are given 2.5 weeks to do it. I mean, you do half a problem a day, you'll finish it, right? Don't keep it in the
What date was that due by? Sorry, was that by
the next, today is
the 11th.
Tuesday. Today is 11th. So I'll probably give you towards the latter part of the month. All right? Definitely. Definitely more than 2 weeks. More than 2 weeks. I'll give you more than 2 weeks. Because the thing is this, not that I want you to rush and do it. I want you to learn from it, right?
Yeah.
So that when you come for the exam, you're fully prepared. At least if you're, last 2 weeks, if you're left with about 10% to revise, then you have no problem. When you have to go through all these sections that we did before, especially the assignments, the mid-semester tests, go through them. And then you'll find one other thing is this, don't try to memorize. What's the point? You have the textbook with you, you have lecture notes with you. You must know which formula to choose, what you're dealing with, right? That's the point. So you go through all these problems, what we did today. Not tomorrow, I start with surface integrals. That's also easy, quite easy, but there's lots of problems I did there. So that I don't want you to do this last question we went through anyway. Someone posed that question to me, I thought we better do it. So we have all these things to go through. Maybe I'll add a few more questions. But this one, this lecture note, I'm going to post it. So where there are errors, you fix those errors, all right? Okay? Okay, you do that. Shall we stop or what?
Yeah, have a break.
Yeah.
Thanks.
Yeah.
Thank
Okay.
you.
Then
I
Thursday.
think I've seen some of this inside a pyramid in Egypt. Raz.
You made my day. You made my day. I really wish for some humor, you know.
Yeah,
There's
yeah,
no comedy on TV. Everything is so serious, you know.
yeah, that's right.
Yeah. I used to wait for Faulty Towers, but they don't show it anymore. But
Yeah.
I really like John Cleese, you know. He really makes me laugh. Wonderful guy.
Thanks, Dr.
Okay.
Reyes.
Have a take care. Take care.
Thank
See
you.
you. See you.
Bye.
Bye. Bye.